And the particular aspects I'll be talking about are related to ignition, reaction, and safety of energetic materials. As always, there is a little bit of background material at the beginning, and then I'll discuss some aspects of research with which I've had contact over the years. So when we think of energetic materials, we can think of different reaction pathways. And this slide here shows some of the main considerations and some of the main mechanisms. So we have a material type and composition, melt cast explosive, or a polymer bonded explosive, or a propellant. And there are different ways in which reaction can be started in these materials, through simple heating of the material, impact, scraping or friction, shear, loading in the system. All of those have been shown for many years to produce hotspots in the material, which start to burn or deflagrate. You get a pressure buildup, and that can lead to detonation, and that is called DDT. But this is an area I'll present some slides on. And then the other main way is to go straight for a shock loading of the material. And this I'll be showing in the form of a gap test, where you put a shock wave directly onto the material and cause a very large temperature rise and the production of very large numbers of hotspots, which produce a shock wave quickly. Some people will say instantaneously, but I'm just going to say on the time scale of sub-microseconds, you get reaction and growth of a detonation wave in the system. So some basic definition of the use of terminology in English for explosives. So high explosives detonate, so high order explosives detonate. Propellants, pyrotechnics are low order explosives. They burn or deflagrate. It can still be a very violent burning or deflagration. High explosives are initiated, that means detonation, by a shock wave. And propellants can be ignited by a flame. Now, these are okay in terms of general classification. However, one important thing that's come out over the years is that in some cases you can get a high explosive to burn. If it's in unconfined conditions and not able to self-confine, it can burn quite easily and without any danger. However, it has also been shown that if you get a fragment impact or if you get a damage in the system, that propellants, for example, may detonate. So although we try and design our energetic material systems to be safe and obviously give us the output we require, sometimes under conditions of hazard, we will find that they will behave in a way which we do not like at all. So one of the main mechanisms I've mentioned there is hotspot formation, and this material will be familiar to those who've seen some of my lectures in the past and also lectures from the University of Cambridge. And basically, hotspot formation is a subject that was studied and is studied, but was studied initially in the 1930s and the 1940s in the UK and in the United States and in the then Soviet Union. And so it's a particularly interesting field. In the UK, it was actually two Australians, Philip Bowden and Abe Yoffe, who were involved in the research in the 1940s to the 1960s. And then the late John Field, who studied hotspot formation and reaction and fracture mechanics in materials from the 1950s until the year 2003. So the whole idea of hotspot theory in the UK came about through studies on friction. It was known that all crystals had asperities, and it was known through friction studies that these asperities, these points, touched one another, And in those points, when you have two surfaces in contact, you get very localized high pressure, elastic deformation, and plastic flow at the very points of contact. It was known that this type of system produced energy concentration. It was also known that if you heated an explosive, you would eventually get it to detonate, to react, and you could calculate the energy required to get that explosive to react. And the energies calculated there were quite large, but also when people took an explosive and put it in a drop weight system, you could get it to explode. And again, you could calculate the energy of the drop weight, and you would find a very big difference between the amount of energy required by heating and the amount of energy you were delivering in the drop weight. So there was much lower energy in the drop weight. And this meant if there was a reaction, and reactions are a function of mainly temperature, there had to be a mechanism where temperature was concentrated. And this was why the people studying friction became interested in the reaction and growth of in energetic materials. So mainly this is the idea they thought of. There are points in contact, and those points in contact are where energy and temperature by association are concentrated. They studied this by adding grits to PETN. PETN is a very widely used energetic material, pentyl tetranitrate. And what they did was they added in a friction assembly different grits to PETN. And you can see the various columns here. So hardness of the grit, and you can see ranges. It's obviously generally in the range of 3 to 4, 2 to 3. This is very common in materials. And you can see the melting point. Now, obviously, we've arranged this table to show a particular function. And what we can see here is that if we look at friction explosion efficiency, we can see that there is a very strong correlation between friction explosion efficiency and the melting point of the material, with the exception of rock salt towards the bottom. So what this indicates is that the presence of these hard material which rub against one another, which increase the amount of friction in the system, increases the friction explosion efficiency if the material can get to a temperature of, say, 500 degrees centigrade or 430 degrees centigrade. Basically, something in that range is where the hotspot mechanism becomes dominant. If you're getting friction temperatures of the order of 330, 320, a couple of 100 degrees centigrade, then you will not get a very efficient system, and you will not get extended reaction. They extended this to look at impact explosion efficiency as well. So you add these grits and you see what happens, and fundamentally you see that there is a similar but not so extreme dependence upon explosion efficiency. But again, you see you have to get above temperatures of around about 500 degrees centigrade in terms of melting point in order to get a reasonable percentage chance of having an explosion. So whatever this energy concentration mechanism is, you have to get to 500 degrees centigrade. This led to more study, and the idea of various ignition mechanisms came around. And so we're talking about research that was published 70 years ago now. It's getting a long time. The original research was done in the 1940s, but was classified for security reasons and eventually emerged in the late 1950s. The whole thing I've talked about, bulk heating is insufficient, energy is localized at hotspots. You put some kind of stimulus there, which interacts with the inhomogeneity, producing the hotspot. Now, the kind of conditions they discovered was the physical size of the hotspot has to be between about 0.1 and 10 microns. And in most of the impact and hazard conditions you find, the duration of the stress, the duration of the mechanical stimulus is between 10 microseconds and a millisecond. And the kind of temperatures you need to reach are of the order of 700 Kelvin. If you can get above 700 Kelvin for longer times, then yes, you can cause things to react, and that would be heating of the system would be the thing. But in terms of mechanical stimulus and low energy processes, then these conditions will help you get a sustained reaction. You can think about different mechanisms, and many exist, but only a few of them form what are called critical hotspots. So these are hotspots where the reaction extends and grows. So here are some mechanisms of hotspot production. There's friction. Well, we've mentioned that already. Yes, it's a very clear mechanism. There are collapse of gas bubbles, where you have adiabatic heating of the gas, shocked focusing within the cavity, and viscoplastic work. Of those mechanisms, mainly the impact due to viscoplastic work, the impact within the bubble is the main feature. You've got things like shear band, viscous flow, and fracture. And when fracture happens, there is generally a stress and temperature concentration at the tip of the crack. And you'll also get some gas produced as well. Electrical hazards, very widely known. So yes, apathy. Friction, in terms of rubbing, in terms of triboluminescence, well, yes, you can get sparks there. Fission tracks, dislocation pileups, thermal fluctuations in the lattice, cosmic rays, all can produce energy, deposit energy into a crystal. However, of those different mechanisms, these are the ones that actually form into the hotspot. So friction, gas bubbles, adiabatic shear, and electrical are very much key mechanisms. Viscous flow within the material helps, but since viscosity tends to decrease as temperature increases, then you find that it contributes, but it's in itself, it's not a critical mechanism. It will help those other mechanisms reach a certain level of energy, concentration, and therefore reaction. But if you just got viscous flow, generally it's only a component contributing to reaction buildup. And then fracture. Fracture is very interesting because if you have a single crystal of explosive, if you look at its surface energy, you'll get the idea that it's actually quite low. It's only a few millijoules per meter squared. But if you add the grits, or you have a tough propellant or a polymer bonded explosive that is, say, below its critical glass transition temperature for the polymer, then you can get a lot of joules of energy out of that process, and then it is possible. So fracture of individual crystals tends not to be an issue, and we have some slides of that. However, if you can get shear into that crystal, if you can get extensive motion and rubbing of the fragments of the crystal, then you can cause reaction to break out. So these are the mechanisms I've mentioned, the subcritical mechanisms. Basically, their size is very small and the energy is leached away from them very quickly. So they tend not to be useful as hotspot mechanisms. I'm sure you could probably find some extreme conditions where you could make this happen. However, in most situations, these things have very little influence. Now, I mentioned when bubbles were collapsing that I said there was a viscoplastic work and shock focusing. So here is a high-speed photographic sequence of a hole in some gelatin, and it's been impacted by the gelatin's been impacted by a flyer. And what we see here through that sequence, which we can follow from top bottom, so it goes from on the left top to bottom, then on the second column top to bottom, then third column top to bottom, etc. So you can kind of read along. What you see here is the fact that you get the shockwave coming in from the left-hand side. It causes motion in that bubble. It drives that bubble, and you get what we call involution. So it swaps its shape, changes its shape from bending outwards to bending inwards, and you get a jet of material formed within the cavity that strikes the far side of the bubble, the downstream side. And that is that impact, it helps propagate the reaction. It produces high pressures, high temperatures, and you've also probably got some heating of the gas as well, so it can entrain some hot gas. But the main thing is the shock of the impact on that downstream side of the bubble. Here is an example of what happens. This was an experiment done by another person in Cambridge called Manohar Chowdhury, and you have a bubble on a silver azide crystal. Silver azide is a relatively sensitive primary explosive. If you hit it with a hammer, it will definitely go bang. So we have a silver azide crystal in a pool, surrounded by water. It's in a tank of water, and there's a detonator in there as well. And we operate the detonator, and we cause a shock wave to move through the liquid. And this is what we see in the slide in image 2. The shock wave coming in from the left-hand side, sweeps across, and at different points in the sequence, you can see how it sweeps across and interacts with a bubble that is on the silver azide crystal. If you follow the sequence, you see the shock wave has gone by, and then as that bubble collapses and as that jetting occurs within the bubble, you get in frame 10, indicated as S1, that is where the impact has happened and reaction has started to build up and grow in the crystal. So quite nice evidence. If you repeated this experiment, but put the detonator on the other side of the silver azide crystal, so you put the detonator on the right-hand side and sent the shock, so it collapsed the bubble, but in the direction away from the explosive crystal. So you're pushing the involution, the shock focusing in the direction away from the crystal. You do not get reaction. So just having shock waves in itself doesn't really make a difference to this particular crystal, but having that impact due to the collapse, involution, shock focusing of the crystal hitting onto the crystal surface, that has a big effect. When we look at fracture, I've mentioned, you've got these different surface energies, and here's a listing of them, basically showing that explosive crystals are not that reactive, don't have particularly large surface energies and are not that reactive due to fracture. Let us show an example of this. This gives you more ideas on PBXs and the fact that if you make the binder very strong, then you store up a lot of energy, and when it breaks, you get a very large energy release. But let's have a look at some examples where we abuse explosive crystals. So here we have a very small sphere, around about 1 millimeter in diameter, hitting a single crystal of explosive, and it's coming in at around about 100 meters per second, and it's striking that explosive crystal, and it smashes its way in this high-speed sequence. There's a lot of jetting of material, etc., but no ignition. You can tell me if you hit it with a larger diameter impactor at a higher velocity, etc., you can get reaction, and that is absolutely true. But what we're showing here is the simple act of causing intense localized fragmentation of the crystal does not necessarily produce ignition in the material. Here is another example. What we have here is a crystal of silver azide again, and this time towards the bottom of the screen, so hopefully see the cursor here. This is a little shim. It's a layer of metal, very thin metal. This is explosive crystal on one side. This is another explosive crystal on the top side. And what we do is we detonate the lower crystal, and this sequence shows it kind of reacting. Because of that metal shim, the hot reaction products cannot interact with the crystal on the upper side of the photo. So this detonation occurs, and you can see through the shim we transmit the stress wave, and there's a lot of fragmentation going on in this crystal, and again, no ignition. So again, fracture in itself is not causing a particularly large problem. However, if we go and do a third experiment, and in this case we have a silver azide crystal, and now we load it in shear. So we're going to basically push that side of the crystal down, and we're going to push that side of the crystal up. So we put it into shear. So one side of the crystal is being pulled down, the other is being pulled up. So it's going to put shear into that crystal. We get some loading, and then we get fragmentation. And here we see the fragmentation has happened and gone all the way through. But then, as that shear happens, as those fragmented crystals are basically rubbed against one another, we get reaction building up and growing through the system. And all of these experiments were repeated a number of times to show the general trend of no reaction just under the conditions of intense fragmentation, and significant potential for reaction if you have a shock involved in the system. So this is quite important in terms of understanding what is going on in terms of the different mechanisms. The area that John Field particularly concentrated on was adiabatic shear bands. This was not mentioned or researched in the initial papers of Bowden and Yoffe. However, as knowledge of shear bands spread throughout the mechanical community, throughout engineering and science, well, we have the idea that there's an impactor happening, and in some areas of the crystal there is thermal softening of those parts of the crystal, allowing more easy deformation in those regions, producing these areas of localized shear where the temperature can go up quite significantly. And if you've got adiabatic shear bands, and generally they turn up in lots of them, not just individual shear bands, adiabatic implies there's very little time for energy to leave the system, and therefore you can get these significant temperatures. You can look at that in a drop weight. We've seen this image before, and here we show shear band formation in a small charge of PETN with a drop height of 1.3 meters. We can see these lines in the system. These are the shear bands, and you can see reaction building up through the presence of those shear bands. And you can also find shear bands in things like HMX. So this is a way of establishing the background that there are a number of mechanisms that are important in the area of reaction and growth in energetic materials. So now we're going to look at some studies basically covering a wide range of impact and loading conditions, but ultimately showing the interplay of those different mechanisms. Now, in these experimental studies, we will follow a general procedure of going from looking at the structure of the PBX, then studies showing hotspot formation, then studies showing deflagration to detonation transition. So we've got material, we've got a stimulus. What does that stimulus do? We've got these hotspots formation, then we've got burning, and then the last examples will be mainly in the area of detonation. So we're going to gradually kind of increase the violence of the system. All of these are relevant to safety for a number of reasons. So one of the first questions is, when we have a polymer bonded explosive for PBX, what is its actual structure? Now, for many people, they try to understand the mechanical properties by using a combination of knowledge of the explosive crystals and the behavior of the polymer. And many times they found that the polymer bonded explosive was significantly stronger than what they expected with their relatively simple models. So we went and looked at the structure of a polymer bonded explosive in close detail using a thing called an atomic force microscope, which basically is a very sharp probe. In this case, it's kind of 4 microns high, that is brought close to the surface of a sample, and it interacts with the material. There's an electrostatic potential caused by the presence of chemicals, caused by the presence of electrons. There's electrostatic potential develops between the tip and the material in the crystal. And what we do is we oscillate that probe. We oscillate that probe and we measure the frequency of that oscillation and also the time of that oscillation. And we compare that to the stimulating frequency causing oscillation and the oscillation of the tip of the probe. And if there is an extra interaction, i.e. with the surface at the tip of the probe, there will be a amplitude and phase difference between the tip of the probe and the stimulation that's causing that probe to oscillate. So this is kind of what the tip looks like. We basically used a silicon nitride base chip in this case, and it was coated with a very thin coating of aluminium. That was again to avoid any kind of static potential buildup in the system. And there are a couple of modes of operation. You can have contact mode where the tip touches the surface and you get deflection of the tip due to surface repulsion, or you have non-contact where the tip is near the surface and you're only probing the variation in the attractive forces between the tip of the AFM and the sample. In all cases, you're looking at tip deflection. So this shows the basic idea of the setup. You have a laser shining on the tip of the probe, a mirror, and a photo detector with a couple of channels, and you compare the intensity of the beam in those channels. Absolutely fine. And you then go put it on your sample. So here is a general view of a very large explosive crystal. I mean, look at the scale here. We're talking in microns. So this is a one explosive crystal, and this is the binder region. And you can see these small areas of smaller explosive crystals within it. If you look at the surface in terms of the range of material on the surface, you will find that there is a small range in the amount of material, but basically it's either binder or crystal, and this represents the crystal areas, and this represents the binder areas. But if you look within the binder, within a close view, and here we're looking over a range of 1 micron by 1 micron, we find these different materials. Now, this side here, this is showing surface height. This side here is using the phase difference in the oscillation of the tip caused by the surface. And that is good at identifying different chemical materials present. So in terms of surface area, you can see there's a few little things kind of stood up out of the surface, but by and large, there's not a terrible great deal of detail there. Over here in the phase system, what we see are these small regions of material, and these regions which seem to be quite dark. Now, when we study this in a bit more detail, these regions here are hard regions, and these black regions here between them are the relatively soft regions. So what we are in effect seeing here are very small amounts of small size explosive crystal grains caused by abrasion of the crystals during processing that have been included in the binder. And these areas here are softer material, either caused by incomplete reaction or due to the lack of stiffening effect due to the presence of these small amounts of explosive crystal. Now, Some people call this effect dirty binder, implying that there is some kind of contamination within the binder which causes the stiffening. I personally disagree with that kind of title because we decided as humans to put the explosive crystals in the polymer and then process it. And what we're seeing here is remnants of explosive crystals. There's no real other components present in the system. So these explosive, fine explosives are stiffening the binder, important point, mechanically stiffening the binder. And that is why simple models just using pure binder as the mechanical component tend to get it slightly wrong. Depends upon how you produce your material. But if you're going for highly loaded PBXs, then you will get this kind of inclusion of the these debris from the crystals into the binder. And that is why these simple models, simple predictions do not work very well. Okay, so the PBX structure itself can be quite complicated. So let's have a look at the next thing, which is producing hotspots. So it so happens that HMX, the high melting explosive, which is often found in production of RDX, is subject to a phase change. And what we find is that there is a delta phase of HMX, which has this property that it has an optical effect called frequency doubling. It fundamentally interacts with the incoming light, and some light is emitted where the frequency has been changed, has been doubled through this kind of quantum mechanical interaction. So it's called secondary harmonic generation. So we have beta HMX, which is which is in terms of the space group, it's a centrosymmetric system, and we have the delta form, which is non-centrosymmetric. That's the thing that helps cause a secondary harmonic generation in this particular case. So we take our beta phase, which is inactive, we impact it, and then we flash a laser, which is in the near infrared region, at the explosive material, the impact, and the delta phase will shine up. Now, delta phase is a high temperature phase, so we will be able to track the formation of delta phase and have a kind of thermometer showing that there is a high temperature in certain regions, and then see if those regions are associated with hotspot breakout. Now, there is also another factor here. If you take HMX and you should drop it in say you make a polymer bonded explosive, or you've got a compact of HMX and you should drop it or hit it or otherwise introduce some kind of mechanical force onto the system, depending on how much force and for how long, you can produce delta phase within the HMX. The delta phase is quite impact sensitive. So if you take a polymer bonded HMX explosive and you hit it repeatedly, you can develop a delta phase, and you will, through just the presence of that delta phase, increase the impact sensitivity of the material. So this has safety implications for highly loaded HMXs, and it's also of interest in terms of the reaction and growth within those hotspots. So beta phase is a centrosymmetric molecular structure. It's in a chair, whereas the delta phase has a boat configuration, and it's quite efficient in terms of generating secondary harmonics. And this means, using this nonlinear optical phenomena, if we put in 1064 nanometer light, we will get 532, i.e. green light coming off, and we can get that kind of light from a neodymium YAG laser. So you can track the presence of this delta form. So here is the camera, there is the drop wave coming down. We have a splitter on the system, an optical splitter on the system. We have a laser mirror which is transmitted to visible light, and we have a filter in the system. So when that impact happens, the laser pulse is flashed. Some of that light goes to a camera which sees the laser light and the visible light, and the other one goes to a 532 nanometer filter, and it sees only 532 nanometers. So the top camera will see laser light and reaction, and the camera on the lower end will only see frequency doubled light. And when you do this, and you do a laser pulse 10 milliseconds before ignition breaks out in the drop weight, you can see some broadband emission. That is on the left-hand side. That's a 4 millimeter field of view. On the right-hand side, you can see a little flash of light from showing the secondary harmonic generation of the delta phase along the crack. So you're actually seeing this high temperature delta phase that is in the HMX. And you can flash 8 nanoseconds before ignition, and you can discover broadband emission again, and you can see the small amounts of light from the secondary harmonic generation in the system. Now, in both cases on the upper side, we can see that we have the laser pulse is indicated by this kind of pink line here. The photodiode is showing the global reaction, but we can clearly see the response of the system in terms of detecting that this secondary harmonic generation is occurring before widespread reaction in the system. So you can see that delta phase is formed in this HMX before reaction breaks out. So we're showing energy concentration, showing that hotspots are associated with this high temperature. Well, we knew that already, but also we're starting to probe the structure and the chemistry of the material affected by this high temperature pulse. So that's in a drop weight. What if we go even higher in terms of our stimulus? So we can do hotspot studies using impact, and this shows a experiment I did with students in about the year 2001. Basically, we have a granular bed of, in this case, ammonium nitrate. We have a copper, we have an impactor coming in, have a glass window, and some high-speed photography, and we've got a photodiode system. And this is what we see if we impact at 700 or so meters per second. You have seen this image before. It shows a false colored field of view. Basically, what we have here is some regions of quite intense light where reaction has broken out. We can count the number of them. It's on a very fast time scale, and we can see how they are going up and grow. Absolutely fine. If we look in more detail, you can see regions like this, which reaction continues to build up in. So this is showing hotspots which actually grow. Whereas here in this region, we have a hotspot which is actually starts to form, and then the energy dies away from the system. So on this fast time scale, we'll see hotspots which evolve and cause extended reaction, and we'll also see hotspots which form but then die out. So we can see critical and subcritical hotspots. Again, interesting in terms of the ignition mechanism, we can actually start counting the number of hotspots. Many models that are used try to mimic this phenomena, but some of those models require a hotspot within every single explosive crystal in order to match the experimental data. From doing studies like this, we see, well, actually, that's not particularly true. You get hotspots and they may communicate with each other quickly. However, you certainly do not see hotspots in every single crystal. So once a hotspot has started burning, once you've got more extended reaction, then you can go through a deflagration to detonation process. And here we show what is happening along a line within the bed of an explosive. So this represents the distance along the bed. Here we have some burning on the extreme left-hand side, and that burning in that bed of material causes a compaction wave to move through the bed of material. That is a granular bed of material, so we've got that little low pressure compaction wave. We have a burning front coming through. It's releasing high pressure gas, and that forms the convective limit system. So that's that line there. That's where the hot high pressure gas has got. However, what is happening is as that hot high pressure gas pushes into the granular bed, you get compaction, further compaction within the bed, producing an impermeable plug of material here, which is pushed forward into the bed, and that causes effectively a shock wave to build up. And on the front of that plug, you have a lot of hotspots formed very quickly, and that leads to effectively a shock to detonation process. So that is an example of hotspot formation and deflagration to detonation transition inside a granular bed of material. That is the general description I talk about here. Let's see what happens in reality. If you've got heterogeneities in there, then you'll get reaction at the compaction front as well as behind, and you get a more smooth growth to detonation. But the basic principles are the same. You need to get this compaction formed and produce that plug which you drive into the material. So here's the experimental study. We're using PETN. We've also used other explosives in the system, and we've got a gasless pyrotechnic igniter. So this shows the confinement of the energetic material. We have this pyrotechnic here. There's a metal shim, and that stops hot product gases moving into there, but it will allow this area here to become very hot, and that will cause the reaction, the burning, which will build up and grow. We use streak photography, and we look at the confinement afterwards. So we're going to ignite here. We'll generate a lot of heat. That heat will cause reaction to start up here, burning to start here. We've got a fiber to tell us when to trigger the camera. When we get light from that fiber, and off we go. And there's a witness place at the bottom, and we can look at the witness place to estimate the severity of the reaction. So that's the experimental arrangement. You've got your camera, you've got your fiber, your delay generator, trigger box, and a extraction from the fume hood. And what we have here is on the top, we have the image that we're looking at. We're looking at a line along this axis here, and we get the system to start burning, and we get that buildup of reaction. You can see that buildup, and what we see here is this little overdriven stage caused by extra compaction of the material due to this compacted material having a higher energy density, so a higher detonation velocity, and then the thing settles down into a steady detonation. So this photograph is in the negative. What we see is this accelerating deflagration. We see a rearward moving shock. We've got this overdriven detonation, and then the settling down to a constant detonation velocity. So this kind of indicates the kind of deflagration to detonation process. That's at one particular density. You can then pick up the confinement, and you've got this deflagration point. You can see that there's some expansion there, and then where the detonation broke out, there's generally a kind of smoother region of metal associated with that plug of material, actually, and that is the extra expansion you get due to that detonation. So that's looking at the witness plate. This is what one of the samples looks like, with the slit in the window that we look down in order to observe what's happening within the material. Now, everything is good, and we use our system to study the buildup of deflagration to detonation in these energetic materials, and we see we've got this slow conductive burning, convective burning, plug formation, and away we go. However, in the early 2000s, we were approached to study some very fine-grained energetic materials. They were produced by a supercritical fluid technique, and they had grain sizes which were sub-micron. When we studied them, we found some unusual phenomena, and we checked in the literature, and we found that in Russia they'd done some work on what they call type 1 DDT. This is what we see here, and this is the kind of output you see from type 1 DDT. This fine-grained PETN with a medium density, you get reaction starting at this case at the bottom of the cylinder, building up in different steps in a generally standard response. Absolutely fine. What we found though, with this very fine-grained material, we could start the tube burning at the bottom, but the detonation happened at the top of the tube. So at the side, well away from the ignition point. Also, the slope of the line indicated a higher detonation velocity. So there was something quite strange going on here. We repeated this experiment a number of times, and we produced this kind of data. So what we have here, firstly in the graph, we have a upstream fiber and a downstream fiber, and this is represented here. So we have our optic fibers at the top and the bottom of the system. We have the burning that starts, and what we see here is from the optic fiber. Well, you know, this fiber here sees some burning relatively quickly. We get build-up of reaction, and then we one that's fully ignited. That's great. Then we see burning at the top of the cylinder, and then we get into the region here, which is covered by the high-speed photograph, where we see that all of the system is burning, and what we get is a sudden breakout of reaction at that point B. So this indicates that there has been no plug formation in the system because the material is too weak to support plug formation. And also everything is burning, so it's quite hot, and that shows the increased reaction and hence the increased detonation velocity in the system. Now, in Russia, type 2 DDT had previously been seen in tetryl picric acid and some propellants. Convective burning is dominant, compressive burning is absent, and the detonation is preceded by a rapid pressure buildup, which in one region, which causes the detonation breakout. So by changing the density of the material, you can have an effect on it, and an effect on type 1 or type 2 DDT, particularly when you're working with new material types, a fine-grained material, then you can get these unusual effects. So going on from that slide is out of position. I'll just point it out. That was the conclusion for the hotspots in the delta phase. Apologies for that. I'll send the corrected version. In this one, we then move on to shock sensitivity. So we've done impact ignition, we've done deflagration to detonation transition. So we'll now do some shock sensitivity using a small-scale gap test. And gap tests are used quite widely in safety. And this is a particularly small-scale version that we've used for many years, where we have a perspex confinement and a solid block of PMMA on the top, and then a detonator off of that. And what we have is the detonator goes off. We have a strict camera looking down this axis, and we follow what happens below that gap. So working with the conventional PETN, so this is in this case, the grain size of material is about 180 microns in diameter. We can make columns of these things, and we can we can put them on and test them for sensitivity to shock pressure from the detonator in the gap test. And so if we have a thickness of gap, which is 3.63 millimeters, we see a little bit of overdrive at the top of the system, and it settles down quite nicely to a fixed detonation velocity, and then the detonation reaches the bottom of the column and the metal plate there, and that's why there's a bit of light there. So what we're seeing here is your fairly standard detonator gives an impulse to the top of the column, causes shock loading, causes shock to detonation transition, and you get a degree of steady detonation on the material in the column. If you make it slightly thicker and you go to 3.67, you see you have this gap here at the top. So the detonator was set up at that point there. You then see at some distance down the column that you get the detonation breaking out, and you have got this reaction going back up into the unreacted material at the top of the column. So what we're showing here is an increased run distance. So the run to detonation distance is a measure of safety. It's also a measure of operation. And when you start to see significant run to detonation distances, you're implying that the detonation is on the point of failing. So if we do a little bit less stimulus, we will get no reaction. This thing here, this line here, is a technical thing called a mistake when we were putting the film into the camera. However, going from 3.63, 3.67, you can see the hooking at the top of there caused by this run distance. And then going to 3.71, no detonation at all. Now, the important thing from these slides is that if you look at the thickness of the PMMA, we've gone 3.63 millimeters, and then we've all gone a whole 0.08 millimeters thicker, and we have no reaction. So we can define the shock to detonation threshold with very accurate values. And so we've got limited go-no-go crossover. We can show that there is a value of stress above which you will get this shock to detonation transition. And by careful preparation, what we mean is those columns were pressed in very small incremental heights. They're 25 millimeters tall. We started pressing the column using a 0.5 millimeter amount of material, pressed it down, took it out, put in another 0.5 millimeter of material, pressed it down, took it out. So they all took like 100 or so pressing operations to produce a single column, and that gave them very consistent density. And because of that consistency in preparation, we could get the very limited go-no-go crossover. So that was good. However, you can, having got that technique established, you can now start applying it to materials produced from different processes. So we did some Arg Sensitivity Studies. So here we see 3 images showing crystals of around the same size produced by different manufacturers. What you see on the top left-hand side is a number of crystals in an index matched fluid. So we're just looking at the voids inside the crystals. Inside this crystal here, you can see there is a large number of voids. Inside this crystal here, there are fewer number of voids, and inside these crystals here, there's 1 or 2 voids. So we can, using index matched liquids, look inside the crystal and see what is happening there. And we can put those crystals into the gap test and measure the critical gap thickness. So the voids inside the crystal, we had a student who counted the average number of voids and the average crystal size on hundreds of crystals. It took them quite some time. We also had surface studies of using environmental scanning electron microscopy to see the morphology of the surface. So that shows 7.9 millimeters for that one. And then this one shows 8.3. So this means this 8.3 millimeter material implies it is more sensitive. But you will notice that the average voids per crystal has gone down. And then if we repeat that with another material, again, it's 9.3 millimeters, that is even more sensitive, and that has got 9 voids per crystal. Now, if you come from a background that says voids equals hotspots equals reaction, you will say this is wrong. The material with the large number of voids must be the more sensitive material. However, we must remember that hotspots is one of several mechanisms causing reaction to build up. In this case, it was ultimately found that it was not the voids inside the crystal that was important, it was surface defects. The number and density of surface defects on the outer surface of the crystal was the controlling factor. So if you wanted to make the material low, higher safety, less chance of reacting, you had to control surface crystal defects and not internal voids in the system. And we showed that for a range of size as well. Here we have type 2, just a slightly different production mechanism, with a much smaller crystal size. And again, average crystal diameter is 29 microns, not 29 millimeters. That's a font change. I will change that as well. Again, you see that the system with the smaller number of voids is actually more sensitive because it's not the voids, it's the surface defects that are controlling the reactivity. So getting on to the very final part of this presentation, we look at cylinder tests. You use them for doing the shock equation of state. And in this case, we used a high-speed camera and also a velocity interferometer system. That is the rough setup of the system. And there is the picture of the test of the setup. And we have a copper cylinder here. We've got explosive lighting. We've got a diffuser. And we've got a high-speed camera in streak mode that's looking along this axis here. And this is my little visor probe at the bottom. And we can get the streak camera records. In this case, we were putting increased amounts of aluminium into a nitromethane mixture. This is to look at when does the aluminium burn in the detonation of this particular composition. Is the aluminium increasing the detonation velocity? Is it decreasing the detonation velocity? Is it interacting at all? We know that the aluminium burns later, producing a thermobaric effect on the system. So, what is happening? Okay, so we've got these streak records, but also we've got the visor records, and the visor records are working as you see here. This is a time scale of distance, and in the first few microseconds, you don't see much because the streak camera is recording expansion of the cylinder. If, however, you look with the visor, you can see the individual steps of acceleration course of the cylinder by the detonation for the different compositions, and you can therefore see the oscillation of the waves within the cylinder wall, and this gives you better confidence as to your modeling, more data to compare. You've increased the amount of time resolution of the system. And we showed by doing these studies that there was no interaction of the aluminium on the time scale of the initial detonation. Things happened afterwards, but adding the aluminium to the nitromethane basically did not affect the detonation power or the detonation velocity, only having an effect as an inert additive to the system on that time scale. Later on, it reacted in the air. So what I hope I've shown here is that there are a variety of techniques that can be applied to the study of ignition and growth of reaction in energetic materials. These can be used with respect to safety, for example. Some techniques, such as secondary harmonic generation, are very specific material. Other systems such as visor are, can be used anywhere if we want to measure velocity. Time resolution needs to be on the correct timescale for the process that we're looking at, and this provides this data provides input to models, has the calculations, performance, the fundamental science. But the other takeaway from this talk is that there are a number of mechanisms that lead to hotspot formation, that lead to reaction. If you just focus on one of them and ignore the other processes, this means you can make the wrong prediction. Everybody would tell me the crystals with the more voids in it are the more sensitive crystals, and everybody would say, yes, of course, it's clear. However, because we ignore these other mechanisms of friction, fracture, etc., bubble collapse, all these ones, because we ignore them, then we can make the wrong prediction, and that can lead to a hazardous situation. So I will end there. I hope you found some of this interesting, and I'm quite happy to take any questions on the subject matter. And Oleg, I'm going to put those corrections into the slides where there was an obvious mistake and send that over to you. But okay, I'm happy to take questions.
There, Bill, thank you very much for very interesting and very useful in the subject of our project lecture. And let me please to start the discussion concerning with the following questions. It's very nice your historical introduction concerning critical hotspots for detonation ignition in not inertial materials. But may I conclude that because, as you know, due to the several reasons, because this kind of the research during the Cold War were carried out independently, and in Russia it was linked with the name of Hariton, as you know.
Oh, yes, yeah.
Critical hotspots. And my question is the following. Practically, the condition of the detonation ignitions related to critical hotspots is related to the topology of hotspots distribution, of course.
Yes.
Topology. And concerning topology, if we are talking about physical mechanism of hotspot generations, it's in fact localization of deformation or damage. And if we are talking about localization of deformation, it's adiabatic shear bands, as usual. It's true?
In some of the situations, yes, absolutely, yes.
And containing that, my question is the following. Since the main subject in the framework of our project, it's luminescence and sonoluminescence. Just now you could find the paper by Farhat and John Field. I sent this paper to you maybe several months ago, but now I decided to refresh, and you could find in your screen, in your email box, because I sent just now.
Okay.
And my question is the following. When we have planned to observe hydroluminescence in inertial liquid near the boundary layer due to the intensive hydrodynamic flow, it could be also considered in the links with topology of localized shears. It's my questions.
Okay, so when we look at things like sonoluminescence in the material, very many people have looked at what is the formation. So sonoluminescence, you have a bubble that's oscillating, and it gives out pulses of light, and it does so in an extremely regular fashion. And the spectral of the light that's emitted shows a very, very high temperature. And what is the source of this? So at the moment, my understanding, talking to people who do this research in the University of California, Los Angeles, it's one of my former students who's joined the group there. But it's very much linked to the fact it's water. Or there's hydrogen bonding in the system. That seems to be a key feature. It seems that on very fast timescales, the bubble collapses, it involutes, it becomes asymmetric. You get that shock focusing, you get that punching, and you get that adiabatic compression of gas. That's all very much accepted. You're doing this repeatedly, so you're pumping energy into the gas. It gets quite hot, gives you the spectra. But there is an effect when that surface hits against the other one. I had this thought that if you did it sufficiently quickly and did not allow the water molecules to move, so the inertial confinement thing, you would therefore produce other mechanisms for the dissipation of energy, which could include, when I say fracture and cracking, I'm thinking of the cornflower experiment, where you see thixotropic material. The material becomes thixotropic. So probably you've done an experiment where you've swirled cornflower in water and you push it with your finger and it's water. You hit it with a hammer, it behaves like a solid. I think on the fast timescales, you can get shear formation within liquids, because we see it with cornstarch. I love cornstarch. It's not the only material that displays this. So I think water on an appropriate time scale could show similar phenomena. So I think there is the possibility, if you can focus the energy and your diagnostic with sufficient time resolution, that you could see effectively a fracture and the associated energy release within a liquid. But you've got to get the time scale right and the size scale. If it was easy, people would have seen it. In cornflower, it's very easy. But if in water, I think you've got to get the time scale right, and it's going to be very much sub-microsecond. But I think it's possible.
Okay, and just in development of this question, Bill, since you discussed the appearance of the second harmonics, yes,
Yeah.
for the critical hotspots distributions, okay?
Yeah.
Because detonation due to the critical hotspots initiation has similar features with phase transformation, because we need correlation properties to initiate the burning, okay? My question is the following. If we are talking about inertial liquid in the condition of intensive flow at the boundary level, and it could be considered, and if, for instance, hydroluminescence could be linked to liquid elasticity and generation of shear bands according to the plasticity scenario, the appearance of hydroluminescence or more sonoluminescence could be linked to the appearance of the second harmonics due to the capacity. Do you understand the way of my thinking?
So in terms of the HMX, I mean, it is a phase, for sure. It's a phase transition in a solid state phase transition, and it's associated with certain activation energy, for sure. And it tends to happen where you get concentration of energy, of course, to produce that temperature rise. Again, I agree. And depending upon the structure of the crystals you have, you can get it. So, and given sonoluminescence and luminescence in general is associated with some kind of energy concentration, I can see. I think I understand what you're aiming at. So I think the presence of luminescence is a good indicator of the potential for hotspot formation, and therefore you could look at the distribution of luminescence in the system. We have done work using on inert materials, just looking for fractal emission in those crystals, and you can see it, but it's a very low level compared to reaction. But it is possible to see fractal emission. Then I think so. There is, as you said, all of this. The way that we approached in NATO, just to use a word, the way that detonation was studied and approached in NATO over the years was quite different to the way that detonation research was pursued in the Soviet Union. And this meant that what I've found over the years reading the Russian literature, quite extensive, is the concentration on effects such as low velocity detonation, which was tended to be ignored in the Western, so-called Western countries. So I think that was intriguing, and there are a whole number of phenomena which have basically been overlooked or not particularly studied in the Western Europe, in Western Europe and America, because the drive was mainly for the function of the material, the normal function. Where I think in the Soviet Union there was a lot more attention paid to these secondary effects, which can have big consequences if you learn how to control them. So I think certainly that will be an area I'd very much like to have a better understanding of. Because I think there are some of those effects which could be optimized for either function or safety in the system. When people talk about laser igniters, generally they are doing laser ignition by putting energy into a flyer plate system, a very small flyer plate system, or they're absorbing energy into a black material within the explosive. But I think there must be other ways of doing more, doing different forms of light explosive interactions beyond that. So yeah, I think that is an area I'd personally like to know more about for sure.
Okay, thank you very much, Bill. Bill, since I hope that next week we will prepare the seminar along the subject of our project, and I will pay attention, at least in my part of presentation, concerning this paper by John Field and Farhat, concerning sonoluminescence. Maybe if you could find time, you will look also at this paper, okay?
Yeah, I'll do that. And tomorrow we have the last kind of tutorial from me. Sorry, on Friday that's for me. Yeah, and that concerning damage in materials. So that's what I'll also work on as well. And as I've said before, I'm happy to take any questions via email as people feel as people wish. Yeah, not a problem. Okay, Oleg, thank you. And I'll look at the paper by John Field and co-authors, and I'll also give you some feedback on that as well. So I look forward to speaking to people again on Friday, and look forward to hearing more about the seminar. Okay, thank you.